Okay, so hello and welcome everyone. So at the moment, you're probably wondering who or what is Geosphere Austria because you might have never have heard it before. Geosphere Austria is the weather service formerly known as ZAMG, but in the beginning of the year, we were pulled together with our colleagues from the Geological Institute, and since then we call ourselves Geosphere. My name is Liliane Hofer, and for those who may not know me, because it's been a last time since my last weather briefing, I studied meteorology in Vienna and I started working there at the head office of ZAMG. I had then the opportunity to move to Salzburg and I'm now working at the regional office here as a forecaster. I'm also part of the EUMeTrain project team, and another field of expertise of mine is the environmental meteorology. So before I start with the actual weather situation, I would like you to show me where you are sitting at the moment. So from all around Europe, I see. So let's continue. When I'm on shift, I always like to start with the night microphysics RGB, as fog is still a topic over here in Austria, although it's already April. And I think with the night microphysics RGB, you get a good overview over the cloud situation. And the big advantage of this RGB is that you can easily detect the fog much better than if you use just the 24-hour microphysics RGB. If you compare, for example, the area over northern France, you can see here clearly the fog patches in the night microphysics RGB, and in the 24-hour microphysics RGB, the contrast is much lower or worse. Another advantage is that in the night microphysics RGB, you can distinguish fog and low water clouds. As you can see here, if you take a look again, as these fog patches over northern France, they appear a little bit, yellow to whitish, and the low water clouds in the southern part of Great Britain, they appear more yellowish. So that's the big advantage between those two. One big advantage is if you take a look at the recipe, on the green beam you use in the 24 hours microphysics RGB, the 10.8 and the 8.7 channel. The nighttime microphysics RGB is quite similar, but on the green beam you have the 3.9 channel, and this channel gets quite noisy in cold conditions. So if during the cold season the fog can get a quite pixely appearance, and it's also a problem if you look at a really high-reaching cloud, like for example cumulonimbus tops, then this channel gets quite noisy and the image quality is lower. So another feature I would like to show you, you can see here in the 24-hour microphysics RGB, is this, I don't know how to call it at the moment. This feature over here, it's not a cloud. It looks like something in the air, and I will come to that later on. So the night microphysics RGB, as the name implies, is only for the nighttime. So as the sun is rising earlier and earlier now, at the 3 UTC image, you can see the limitations of this channel in the eastern part of Europe over Russia. All the cloud features disappear, and all the clouds look more reddish or pinkish. And that's the advantage of the 24-hour microphysics RGB. You can use it all through the day. And I would really invite you to take a look at the night microphysics RGB during the day, because then all the clouds have the same color. So it's really useless during the day, but it has its advantages during the night. Another RGB I always like to look at, especially at the beginning of my shift, to get a good overview over the current weather situation, is the Airmass RGB. You have here the recipe of it. It uses the ozone channels, the infrared 9.7 and 10.8. So one goal of this RGB is to distinguish the air masses, because if you have an ozone poor air mass, like a tropical air mass, you have a low contribution on the green beam, and it appears greenish, like here in the southern part of the image. These greenish colors indicate tropical air masses. On the other hand, if the air mass is ozone rich. Like polar air masses, they appear bluish or purplish, like over wide parts of Europe. So we have really cold conditions going on. Another big advantage of this RGB is that you can see things like the jet or deformation zones. You can see zones of advection of potential at vorticity, and these appear all in reddish colors because we can see them due to the water vapor difference. And for example, if you take a look at the frontal system over here on the right side of the image, you can see these reddish stripes going into the low, and that is a sign for ongoing PV advection. That means that there's still some development going on. Or over here from Great Britain to Central Europe, you can see some red stripe. And that is the situation, the current situation of the jet. So this is a really powerful tool. One more thing you can use this RGB for is to detect where lower clouds and high-reaching clouds. And I would like you again to take your annotation tools and to mark areas where you think that there are really high-reaching clouds. Okay, yes, it looks good. A really whitish feature. If you compare it to the other clouds, if you take a close look, you see that the different clouds have different shades of white, and the more whitish the clouds are, the higher reaching the clouds. So yes, you can see this frontal system in the east. That looks very impressive. We have also these lee clouds east of Sardinia, and yes, also this occlusion over Scandinavia. You're totally right. So I will show you the solution in the next image. Yes, here you can see the 10.8 infrared enhanced channel, the brightness temperature, and you can see the solution. So yeah, not a big surprise. The whiter the clouds, the more higher they go up. Yes, but it's also a nice feature of the Airmass RGB. And one thing I've told you before, the feature that you have seen in the 24-hour Microphysics RGB, it can also be seen in this Airmass RGB, at least if you know where to look at. So if you take a look at the area between Iceland and Norway, you can see this feature here. It looks a little bit more pinkish than the surrounding area. And thanks to Jochen Kerkman, he sent me this loop. I will start it. I hope you can see it all. So you can see this feature coming in here. It looks like some smoke. I hope you can see it all. It's not that good visible. This is the dust RGB. By the way, it has the same, so to say, ingredients like the 24-hour Microphysics RGB, but the enhancement is a little bit different so that you can see dust a little bit better. So I will play the loop one more time. And you have to look here. You can faintly see this dust plume-like feature coming in here. Okay, one last time. So if you know where to look at, you find it easily, but if you don't, yeah, you can easily oversee it. And Jochen gave me the hint that it may be some volcanic ash in the air. And at first I was thinking volcanic eruption, and I was Googling it and didn't find anything. So I just went back with the images. So I just took a look at all the dust and the Airmass RGBs that you can easily also follow on the ePort. So you have all the images there, you have the GOES images there, and I followed it back, and then I found the culprit, and that is a volcano on the Kamchatka island. It's the so-called Shiveluch. I'm really sure I'm not pronouncing it correctly, so sorry for that. And I was really astonished, because you have to imagine that this volcano is like 12,000 kilometers away from the North Atlantic, and it's also, this event happened like on the 11th of April, so like 2 weeks ago, and the dust plume still made it to Europe, and I think that's really, really astonishing. And I will show you now some images I have found, but I really invite you to take a look at it yourself. So here we have the Kamchatka island, and somewhere here should be the volcano. It's an active one, and due to media reports, the ash cloud got as high as 20 kilometers. And the funny fact is that you can see it here on the dust RGB, the ash cloud, in these bright yellowish colors, but you can see it a little bit better on the Airmass RGB in these pinkish colors. And now you can really follow it around easily. As you can see it here really distinct. That's the 13th of April. So it's going eastwards, and yeah, you really have to take a look at the e-port. There are really some nice images. Okay, Jochen says it's such a high volcanic cloud. And that's also the reason why it's here so long. And now we are on the 22nd of April, 15 UTC images. And I have here a comparison of the dust, the Airmass, and the natural RGB, and you can see it in all three. You can easiest locate it in the Airmass RGB here, but it also can be seen in the dust RGB if you know where to look at over here. And it's also visible in the natural RGB. You can see here this grayish cloud. So it caused air traffic problems over Canada, I assume. I haven't heard of anything in our area, in the European area. And I want to close my presentation with the last image that was available for me in preparing this weather briefing. It's the 9 UTC image from today, and you can still see the ash cloud if you know where to look for it here. North of Norway, you can clearly see it, and yeah, I really invite you to take a closer look at it and to follow its path over Canada to Europe. It's really an interesting case, and thank you, Jochen, for sending me the loop, and for, yeah, I wouldn't have thought of this if you haven't pointed me to it. So thank you for that, and thank you for your attention, and I will now give the microphone and the stage over to you, Christian.
Okay, so I will start right through. First of all, who is this guy talking? My name is Christian Resch, as it was mentioned already before. I wanted to introduce myself a little. I was born and raised in Salzburg, Austria, then studied atmospheric sciences in Innsbruck. My master's thesis was about a retrieval algorithm for aerosols from sky radiance data. And then I also had the chance to go back to Salzburg and work at the regional office of the Geosphere Austria, also as a forecasting meteorologist. And when I'm not working, I really love music. And then I'm most of the time outside somewhere, climbing, backcountry skiing, or road cycling. That would be me. And now we take a look at an interesting event that happened this month, namely the precipitation event from 13th to 15th of April this year. On the right side, you can see a surface chart, which is generated multiple times a day by us, by the Geosphere Austria. And it's also a very nice overview and should give you a glimpse of what we're going to talk about today, or I will talk about today. So what happened? There was a cold front on Thursday the 13th, which passed the Alps. And in the lee of the Alps, we had some cyclogenesis going on. It's a fairly common weather pattern for us in Central Europe. Afterwards, we had a low-level, low-pressure system, which then moved in a 5B pattern over the south and east of Europe and brought a lot of precipitation. And it had a lot of impacts. It was a very complex weather situation for the forecasters because it had impacts for the avalanche risk, dangerous conditions on higher streets and passes, It caused some local floodings, but it was also a bit of an ambivalent event because it also brought some long needed rain for the eastern part of Austria, which was very dry for a very long time before. So just to get over it again, what was 5B again? 5B is a weather pattern for low pressure systems, which originate from the Western Mediterranean Sea over the Gulf of Genoa most of the time, or somewhere in this region, and then move in a northeasterly path into Central Europe up to Poland. And these guys are very known for being notorious precipitation events. They often have, or unlucky not that often, but they do have hazardous impacts. For example, in 2002, we had a big flooding in Austria, which was in terms of a 5B low pressure system, which caused 3 billion euros of damage, fatalities, people died. But as I said before, it's also an important source of humidity for soil and vegetation. And here on the right side, you can see from a publication that was made by the Geosphere, the paths of around 600 5B cyclones. So you can see the path from the Mediterranean Sea over to Central Europe is quite the same most of the time. So for us at the Geosphere, it was quite complex because we had to do a lot of warnings. And it was quite complex because we had we were not really sure about the rain-snow line. So we had to do separate warnings for the two precipitation types. So on the lower part of the slide, on the left side, you can see our snow warning, and on the right side, you can see our rain warning. Because these two different precipitation types have different impacts. For example, in the western part of Austria, there are a lot of mountains. The altitude is a little higher. So in these regions, the precipitation will reach the ground mostly as snow, which means that it's not really going directly into the rivers as liquid water, therefore not causing that many floodings. On the other hand, it raises the avalanche risk, and also higher streets can get into troubles because there can be a lot of snow in a really short amount of time, which can cause traffic jams or car crashes or something like that. On the other hand, in the right half of Austria, in the eastern part, it's very low compared to the western part. So most of the precipitation comes to the ground in liquid form. And this is also the region where we had to give out a rain warning because we expected a lot of rain. And some smaller floodings and small landslides were very probable. And if we take it now, look at the Airmass RGB. I mean, Lily already explained it quite well, but I think we can skip it here. I'll just do the prestigio. So what do the reddish areas mean? As we heard before, it's dry sinking air and downward motion of stratospheric air, which is always an indicator for cyclogenesis. So we can see in the left picture in the Airmass RGB, we can see the cyclogenesis happening in the lee of the Alps. And if you take a look at the right side, at the surface chart again, this is now from the 14th in the morning, we can see that the low pressure system already made its way into a more northeasterly path. And if we take a look at the clouds or the whitish areas, also as Lily explained before, clouds can do well as a proxy for frontal zones. And if we now take a look into the radar, you can see that the precipitation is obviously in these regions. Yeah, and then we can take a look at the different impacts. For us in Austria, it's always very important to know about the avalanche risk, not only because in your leisure time you want to go backcountry skiing or skiing in general. It can be very dangerous if there is a high avalanche risk, because some avalanches can reach into the into the ski slopes, or even onto some higher streets. Fortunately, this did not happen at this event. But if you take a look at these two pictures in Austria, or I guess everywhere, in every country which has to deal with avalanches, we say the wind is the build master of the avalanches. And if you take a look at the combination of these two graphs I'm showing here, we have on the upper right side, we have the wind gusts on Hoher Sonnenblick, which is one of the highest meteorological observatories we have, on more than 3,000 meters high. And you see gusts up to 90 kilometers per hour. And in combination with a lot of fresh snow. If you take a look at the lower left, you can see the snow height in centimeters. And you can see that there is an increase of about 70 centimeters in the course of Thursday and Friday up until Saturday. So the combination of a lot of fresh snow and quite some good wind resulted in an avalanche warning of level 4, which is only, 5 is the highest, so 4 is already quite high for the main ridge of the Hohe Tauern, which is the highest region we have in the Austrian Alpines, in the Austrian Alps. And then on the other hand, we had to think about the liquid precipitation. So as you can see, or as I explained before, in the more eastern part of Austria, due to its low altitude, the precipitation came down mostly in liquid form, which resulted in the quick rise of levels of small and middle-sized rivers. You can see on the left, on the lower left, this is from the hydrological service of the Lower Austria department. You can see that the level of the Erlauf, which is a small to mid-sized river coming directly out of the mountains, had a sudden increase of about going from 180 centimeters up to 2.5 meters to 260 centimeters in a few hours, which is quite a lot. And if you take a look into the lower right, you can see the 72-hour accumulated precipitation calculated from Sunday 16th at 8 local time. So there are pretty high values in the regions where there are more mountains. In Austria we call it Nordstau. So it's because if you take a look at, let's go back. As you can see on the right side, the low pressure system is like turning, and then the precipitation in this case with this warm front is pressed against the Alps, and there some stau is happening, so like some jam pressing against the Alps, and there the most precipitation fell. We had around 140 or up to 140 millimeters in 72 hours, which is quite a lot. Luckily, as I said before, there are mountains, and therefore a lot of this precipitation was held in solid form. However, if you take a look close to Vienna, we also have these dark reddish areas. Unfortunately, there is no legend. I had to clip it, but it's around 100 millimeters in the 72 hours. And as you can see in the upper right, this is an overview on the emergency calls and duties for the fire brigade. And on the symbols, you can guess what's happening. So these are all floodings and winds and smaller traffic problems. So it was a very busy weekend for the officials, because there was as I said before, smaller floodings in buildings, in cellars. Some streets got flooded, but also the motorway, which is going across Austria from east to west here, reaches up to around 500 to nearly 600 meters for a small track. And there we even had snow, so we had snowy conditions on the motorway. And then a few kilometers more in the east, it was again raining like crazy. So it was a very complex situation. And if we now take a look at the other side of the medal, as I said before, the eastern part of Austria had a very dry period going on before. Many groundwater levels were close to a new minimum. If you take a look at the left pictures, you can see these dots everywhere. Unfortunately, it's in German, but I didn't find another source. So the reddish dots mean that it's extremely dry, or the groundwater levels are very, very low. I think it's more easily to see in these graphs. And there you can also see that the dry period was not only weeks before or a few months before. It lasted, if you can see it, it's a little bit blurry, but here in July and August, so in the summer of last year, the Neusiedler See, which is close to Vienna and on the border to Hungary, we had very low, actually new minimum values of the ground level near at the Neusiedler See, Lake Neusiedl. And also right before the event happened. So you can see here, April 23, it was on a very low level. And then the event happened, and only over this weekend, Lake Neusiedl raised its level by 8 centimeters just over the weekend. And there you can get a feeling of how much rain this whole thing brought. And here on the upper right side, I have a small graph where you can see that since February, it was very dry all the time, or at least drier than in the climatological plan, so to say. And then this weekend came, and then suddenly we are above average. But actually, this is from when I made this presentation, it's a few days ago. So we did not have much precipitation since then. And so the graph is already going like straight to the right again. And so we will see how big of an impact this 5B cyclone was. And with that, I wanted to close my presentation. Oh yeah, it's already finished. So yeah, thank you for your attention.